Hello, today I'll be presenting my design proposal for a CVT-coupled flywheel speed controller for the Marble Machine 3 drivetrain. For those not in the know, the Marble Machine 3, or MM3, is a machine being built by Martin Molen of Wintergatan, which is capable of producing music using marbles as well as other mechanisms fully mechanically, with no aid of electronics. In this case, it would be the third iteration, but the second attempt at making one capable of doing a world tour for large concerts. One of the important mechanisms of that machine is the drivetrain, which must be able to keep consistent time and tempo throughout the duration of a song. Likewise, it must be able to do so despite varying changes in the load from the machine from friction or varying amounts of marbles being dropped and lifted by the marble conveyors. Likewise, it also has to be able to handle differences or variations in the amount of energy being input by the musician, given that it is a fully mechanical machine that is human-powered. My design, as was originally discussed on the Wintergatan Discord, aims to provide solutions to this problem of timekeeping, while also providing a few benefits. Firstly, this design will allow the musician to pedal or crank the machine in phase or time with the music, as opposed to the case of the already proposed Huygens drive, which necessarily requires the musician to input energy into the machine at a different rate from the music. And requiring that of the musician would be effectively like requiring them to hop on one leg and rub their tummy and pat their head at the same time. Basically, it's kind of like requiring them to do polyrhythm, and would be rather distracting and prevent them from being able to do other operations or control different parts of the machine. So this is very much meant to aid with the user-friendliness. Another point of consideration is that though the Huygens chain drive is capable of providing constant force, it only does so when you are not imminently trying to charge it, as in it was designed to work with a constant load escapement and to only be reloaded or rewound once every few hours if not days, whereas the approach that was being suggested in that original gramophone governor and Huygens drive video would have had the Huygens drive being constantly wound, which completely defeats the constant force purpose. Likewise, constant force isn't actually what we need because that would not be able to handle the varying loads of the machine. So if the load on the machine decreases but the force is constant, then it will accelerate. And if it increases but the force is not also increased accordingly, then it will decelerate. As for the gramophone governor idea, and to summarize for those not in the know, basically it's like this speed measuring device over here, except that after it reaches a target speed, there is a brake that gets hit, and that basically helps to prevent it from accelerating further, though at the moment I don't know much details on the sensitivity of that and how it relates to the coefficient of friction of that brake. Namely, though Martin was able to demonstrate excellent timing capabilities of that gramophone governor with Huygens drive, we did not test how that equilibrium speed changes with differing input weights or output loads. Likewise, it is currently unknown how well that gramophone governor will be able to respond to increases in the system load or decreases in the energy input, whereby in the worst case, the gramophone brake will have to constantly be dissipating the maximum anticipated energy deficit. In regard to that energy efficiency and the musicians who will have to be powering this machine, instead of dissipating excess energy or dissipating a constant minimum in order to handle deficits of energy, as in the gramophone governor, my design aims to be able to dynamically redirect said excess energy into the winding and acceleration of a flywheel, while also being able to dynamically return that momentum back into the system whenever there are energy deficits. Likewise, this is in contrast to the traditional passive flywheel, which is only capable of reducing the rate of change of the speed of a system, but is incapable of maintaining a specific speed in the presence of varying load and input forces. Now, though a revisit of the flywheel experiment may reveal that close control of a hand crank could actually be tight enough, this would inhibit the musician from being able to do other things. And in mitigating this, one must consider the acceptability of the aesthetic of having a non-musician on the side or behind the machine, whose sole purpose is to maintain in-phase timing of the entire machine, or out-of-phase power input to a separate marble conveyor drivetrain. My design would avoid those aesthetic compromises and enable a unified drivetrain. My design thus instead presents a CVT coupling between the flywheel and the drivetrain, and a dynamic feedback mechanism that will control the torques and forces and transfers of momentum in order to maintain the speed. So for some context, I had originally attempted to design a mechanical PID controller. So here we have a Porter governor that's really acting as a tachometer, and the idea is that as you accelerate, these weights here act against a spring, in this case a rubber band, and that moves this measurement head or sleeve inward, and that allows you to measure the speed. In this case, I wanted to attach this to an eddy current brake. I had later on, again, more links in the description for the original descriptions of the design. I'd come up with a more sophisticated gearing for obtaining the proportional, integral, and derivative control. So again, for more info on what PID control is, you'll have to Google that, but in short, the issue with PID control is it's complicated. You have to be able to generate or obtain the derivative, the proportional component, and the integral. That's kind of hard to do mechanically, since, at least for integration, you generally need what's called a wheel and disc integrator. You can Google that. And one also has to contend with the problem of PID tuning in order to minimize oscillations or instabilities, among other things. So yeah, this one was working with an eddy current brake, so it would have still dissipated energy, whereas this design over here was where I came up with the idea to use a CVT between the drivetrain and the flywheel, just that I was still trying to work out the best way to actually control the control wheel, which is handling that transfer of momentum. Then it was finally here that I came up with a much more simplified version that only requires derivative control, but takes advantage of a very specific CVT setup. So the original design was inspired by what's called a wheel and disc integrator. So you have normally a constant speed disc, then you have your integral wheel that can be translated left and right. So that's this guy over here, moves like so, and you have this guy that can rotate. As you can see, if it's rotating near the center of the lower wheel, this wheel here will rotate slowly, but over here it will rotate more quickly. So that in effect gets the integral, but also can implement a CVT or continuous variable transmission, namely a continuous range of gear ratios. So the fundamental concept then was to think of what would happen if I were to connect the marble machine drivetrain to this lower CVT disc here, and then connect the flywheel, which is normally directly coupled to the drivetrain, but now to instead allow us to continuously vary the gear ratio between the flywheel and the system. So let's say that the system over here was rotating at a certain rate, and hence the flywheel, which is coupled at a certain gear ratio, also collectively together possesses a total rotational kinetic energy and angular momentum. Given that, assuming that I did not add or move any energy from that system, what would happen if I were to move this control wheel left or right, such that there would be a necessary change in the ratio of velocities between the flywheel and the system under control. In that regard, I was able to mathematically predict that there will indeed be a transfer momentum between here and here. So in this case, if you want to conserve energy and momentum, if you move this wheel toward the left, then the energy would be going from the system under control into the flywheel. If you move it to the right, then the energy would come back from the flywheel into the system. So if I could find a way to control this in a certain way that will maintain the constant speed of the machine or system under control, then we would have a very energy efficient control solution. Now, as I will show later on Desmos, I had some confusions with the conservation of energy and momentum, where it seemed like they were somehow not agreeing, but that was really just because I wasn't accounting for the momentum of the Earth to which this CVT mechanism is being coupled. So in doing that, I came up with this arrangement where we instead have two discs sandwiching the control wheel, which is now passive instead of being hooked up to the flywheel, and it turned out that this had desirable properties that make for rather nice control, leading up to this final design over here. So basically now in this design, I no longer required an integration wheel and disk system, and all I'm doing is measuring the rate of change of the error in the speed of the system under control. So in terms of correlating the parts of this diagram to my prototype here, first we have a centrifugal tachometer. So that's basically just a speed measuring device as opposed to like a eddy current drag cup mechanism, which would be lossy. So again, as this guy flies, well, accelerates, your weights will move outward and move a sleeve in order to measure the speed. And let's say that I were to tie this guy down over here in order to select the speed. Then as we accelerate, only once we have reached the target speed will this end over here, this measurement end, move to the left. So if we're hitting this point, that means that we're too fast, and if we're hitting this point, that means we're too slow. So we want it to rest right at the middle over here. That would mean that we are at our target speed. But as you can see, without a flywheel, or even with a flywheel, but at a slower rate, I am not able to easily maintain that middle position. I'm always speeding up or slowing down. And again, if I slide this over here, that means that we have a faster target speed before this guy over here starts measuring the error. And if I move this over here, then we have a slower target speed, as you can see. So another word for the target speed in terms of control theory is the set point. So that's why I call this end over here, or this, the SP head. So when actually using the machine, the idea is that the musician would be able to speed up to the target speed, and once they reach that speed, they would grab a hold of the knob and they would lock it in place. And after that happens, then this part over here would be activated in order to start providing control feedback for maintaining this speed. So again, normally you would start off with this part over here fixed, and using this set point head, which would actually be measuring the current speed of the marble machine as you're starting up at the beginning of a song. Then, once you set it over here, now only this side over here will be moving, and again, if it's hitting this point, that means we're going too fast. If it's hitting this point, we're going too slow. And thus, we need a way to provide a feedback that will maintain this part at the very middle. So this side over here can be said to be measuring the current speed or error in speed of the system, and that would be called the process variable in terms of control theory. So that's why I call it the PV head. So that's this sleeve that is moving left and right by a much smaller amount than when this side over here is unlocked. Then we would have this little pulley here. So here I was using tension pulleys in order to prevent backlash, since any backlash in this mechanism would reduce the sensitivity to any variations in speed. So that guy here would be pulling this pulley left and right, which would be rotating this very small bit over here, and then I was attaching that to what's called a torque amplifier, and that torque amplifier helps isolate the reactive forces of rotating this much larger wheel. In this case, I expect this to be 15 times larger in radius than this small wheel here, since if you have any reactive forces trying to push this PV head, then you would actually have inaccuracies in the speed that you're measuring. That is because the position of this sleeve for any given speed, namely that equilibrium position, is highly dependent on the balance between this outward centrifugal force and the compression force of the spring here, or in this case, the tension force of this rubber band. So on this machine, I instead have this rack and pinion, which I can easily decouple, and that just moves like so. And I can actually do this like so to help reduce any backlash and improve the sensitivity, though there is still going to be some flexure here because it's Lego and I don't want this to be too tight. So that would rotate this guy over here, left and right. So in this original design, I was directly going into this smaller wheel, whereas now I'm already immediately doing an approximately 4 times multiplication in motion from this pinion to this pulley here, which goes into our torque amplifier. So in terms of torque amplification, basically the idea is normally if you want to multiply motion, you could do something like a gearing up as I'm doing here, but as a result, you end up with a multiplication of the reactive forces over here into this area, and we don't want that. We want to be able to isolate the force required to move the control wheel from the forces that are moving this process variable head in order to measure the error in the speed. And for that, I came up with this alternative design to the traditional capstan torque amplifier. So here's a link to a video explaining that. More links in the description for other context about torque amplifiers. But basically, this design here is going back to the original capstan mechanism, namely the powered capstan, where you have your machine, and now we can see these wheels rotating. So basically what's happening is that imagine that you have a larger torque power source, in this case a musician, that is constantly rotating these wheels, one in this direction, the other in this direction. So what happens then is that if I have an acceleration, that will cause this wheel here, or this part of the pulley, to move in this side. That will decrease the tension on this part. And then under here, it will increase the tension. So when we increase the tension here, a small increase with these 4 wraps or loops around this drum will increase the friction upon this drum, allowing us to siphon energy from this power input into increasing the tension on this part, or this pulley. That in turn creates a net torque that will rotate our control pulley here. So I have 2 counteracting strings which are under tension. And likewise, if the system is slowing down, then it will be trying to rotate in this direction. So now the lower capstan will be detensioned, while the upper capstan will be squeezed, causing it to, again, as it's rotating like this, pull on this upper string, causing this guy to rotate in this direction, and now moving this control slider toward, well, our left here. So the reason I employed this style of torque amplifier as opposed to the traditional coaxial one designed by Niemann is in order to reduce backlash and make it easy to adjust the tension of this system. So basically the problem with this traditional torque amplifier is that you have these 2 drums, but you have 2 separate lengths of string or cable that have to be tensioned perfectly so that the counteracting forces will cancel out, else you will have a constant bias rotating in one direction. So of course it would be a bit of a pain to constantly have to adjust that perfectly before every single marble machine show, or even between songs. You don't want that to happen. So with this design, we instead are able to have one contiguous line of motion of string, so that basically if we tighten one of these or the other, then we will always be able to obtain a equilibrium just of the position of this control pulley, and we will never encounter issues with the biasing of trying to rotate in one direction. But in terms of ensuring that this style actually works, you do have to make sure that your choice of string has absolute minimum of stretch, and that it is also very flexible, as if it's too inflexible, then that will in itself incur a form of flex in terms of buckling or unstretching. So, for example, fishing line was not a very good choice for this scale of mechanism. So, as I would have further explained in the build video, this mechanism is in fact quite sensitive, but that highly depends on the string being in sufficient tension with respect to a minimum of stretchiness, as any stretch here will create a greater delay between the input force and the ability to actually put the output load into motion. And any such backlash will reduce the sensitivity and hence accuracy of the mechanism. So in this case, for this design, I'm having an approximately 4 times motion multiplication from here to here. Then I'm having a work amplification or torque amplification through this mechanism, which then drives this wheel here, which performs an additional 4 times multiplication. So I have a total motion multiplication or mechanical disadvantage, but aided by this torque amplifier, of around 16 times as opposed to my original design's 15 times gain. And as such, 2 millimeters of motion here will allow this guy to slew by pretty much almost all the way up to here. So that's pretty nice. As for the significance of this 2 millimeter figure here for this motion, the motion range of the centrifugal tachometer is about 52 millimeters, while the radius of the CVT discs is about 31 millimeters. That so happens to be almost the same scale as my 1/10 scale drawing, where instead we had 15 centimeter radius CVT discs, and our centrifugal tachometer here had a motion range of 50 centimeters, and in that regard it was instead spec'd to have a 1 centimeter range of motion. So in the case that we had a linearized design, because the relationship of the motion of the position of this PV head here, or the sleeve, for measuring the speed of a tachometer, and with respect to the actual angular velocity of this tachometer, isn't actually linear for this basic mechanism. Whereas, like if you do something like this, where you have a cam profile, it is in fact possible to linearize the motion. But anyways, assuming that it were in fact linear, then that means that if you had a variation of up to 1 centimeter in position, then that means that you have an approximately 2% error with respect to the entire speed range. And that would be a 4% error range if you were to be operating the machine at a target speed half of its maximum rate, namely with the sleeve at a position of 25 centimeters. So we can say then that there is a linear relationship between the position of this PV head and the lateral position of this control wheel. As I will later demonstrate mathematically, or at least graphically, it so happens that when you have this relationship and this whole CVT connection, the momentum transfer happens to be such that, let's say that if we have this gain of 15x to this 15 centimeter motion range, that means then that it will actually be impossible, provided that this control battery here has enough kinetic energy, it will be impossible for the system under control to exceed a 1 centimeter motion range of this PV head, namely a 2% error in speed relative to the entire measurement range. So basically then the idea is that with this design, all you need in order to make it even more accurate is to simply increase the gain between this motion here and the motion of the control wheel. So technically, in theory, if you had infinite gain, in this case it's in truth a derivative gain, but where the derivative curve looks like this, and our target speed is at the middle here, then you would in fact have an optimal control solution, where the output speed is perfectly maintained regardless of the input and output loads, and it will perfectly track your currently selected speed from setting this position of the SP head. Now going back to my prototype, my 31mm CVT disc diameter is effectively double the proportion of the original 15 centimeter CVT discs in this design. And that basically implies that if I'm only achieving a 16x gain here, motion gain, whereas here we had 15x gain, then that means I can only get 2 millimeters relative to the 52 millimeters of motion tolerance, so not as tight compared to 1 centimeter out of 50 centimeters. So when implementing this mechanism on a marble machine, if you want to maximize the tightness of the mechanism, namely the smallness of the allowed motion of the measurement head relative to the entire tachometer, either you make the tachometer as big or long as possible, or you try to maximize the amount of motion and torque gain over here in this torque amplifier and these pulleys, or you try to minimize the radius of the CVT discs, though doing that would necessarily require a greater torque capacity or traction out of the omniwheel. So we've already established the linear link between the motion of this PV head and this control wheel. So namely from here, this measurement head, all the way to this control wheel. The question then is of how we will be able to get this control wheel to slide laterally with respect to these CVT discs that they're supposed to be in high traction with, at least in one direction. So one solution is the continuous omniwheel, which I'm showing here. Okay, so under fair use, I'll be showing this here as being the kind of omniwheel that I was talking about. So basically, you would have this specially shaped frame, which allows you to have these differently sized wheels overlapping for almost seamless rolling across the entire circumference of the wheel. And again, with each of these wheels permitting lateral motion of the omniwheel, as in this design. And here's another example of that. Here's another example. So you can see that with these chosen dimensions, the frame would have to be rather thin, hence you would have a lower load capacity, but you could probably optimize these shapes to enable a thicker and hence stronger frame. Here's an example of a commercially available one, around a minimum of $100, though yes, for the marble machine you will most likely need custom ones, so those will be costly, but very much quite crucial to the operation of this mechanism. Here we can see that instead of using a rubber coating contacting a flat bare metal CVT disc, I would rather recommend having bare metal but machined to have these pointed, ideally a bit more even knurls contacting a rubber sheet, in this case maybe approximately 1/16 inch and minimum Shore ATA hardness adhered to the CVT discs in order to maximize traction. You will also need to make multiple prototypes in order to optimize the shape of these knurls. For example, like maybe it would be beneficial to use a diamond knurl instead of these straight annular knurls. So for that we would have to optimize the traction in this direction while also minimizing the frictional losses from this rolling, and we also want to minimize the rolling friction from the perpendicular axis from lateral motion of the control wheel in this direction. Now, I obviously can't implement such an omniwheel in Lego, at least at this scale, and as such I chose this wheel here, which has a nice and almost point-like contact with the neoprene surfaces that I put onto these Lego discs. The issue then is that, of course, there's quite an amount of traction, and I can't just slide it left and right. Mind that actually brings the system to a standstill when doing so. So I came up with this whole sliding mechanism, which is further explained in the build video, which I will link at the end. And that basically shifts this wheel forward and backward to take advantage of the motion. So if it's moving this direction here, so if I want to move it toward the left from this perspective, it will push the wheel in this direction, and since the CVT disc here is also rotating this direction, then this wheel will also process or move like so, and the opposite if I move this slider in this direction, which will pull this wheel backward. But the net thing is that it basically implements something equivalent to this omniwheel, but it will have a lot more delay in between the actual sensing of a change in speed and the actual changing of the position of this control wheel. so it won't be as responsive. So for the construction of these CVT discs, we nominally have both radial and axial bearings. So radial in order to counteract any torsion from this pressure, and also axial to counter the whole sandwiching force upon this omniwheel for providing sufficient traction. We would also have, instead of these flat bearings, rather rounded edge bearings contacting at points along the line opposite to where the control wheel would be applying pressure. But as you can see here with Lego, can't really do that, so instead I had to use these rollers here. And yeah, these rollers do contribute to a decent bit of friction that will prevent this prototype from behaving as ideally as I would have liked. As for why I need these front and rear retaining wheels in addition to the main ones that maintain the pressure of the CVT discs upon the control wheel, that is because as we are running the machine, it will, in addition to applying a traction force to rotate the control wheel, experience a reaction force pushing it in this direction. Likewise, the top of the control wheel, which is trying to rotate the CVT disc in this direction, will also be trying to push it in this direction. And if you remember from my explanation of this whole sliding mechanism I'm using instead of a control wheel, now here, in the event of flexure, that would basically cause the control wheel to be a bit forward of the center line that it's supposed to be operating upon, or sliding about. And because the surfaces of these wheels will be rotating in this direction, it will also be pulled in this direction. And the opposite will happen if there's a slowdown in the machine, and the flywheel is now trying to apply a torque upon the control wheel. So you will have the opposite reaction force trying to push this wheel in this direction, and the control wheel will also be trying to push the lower CVT disc in this direction. And now, because the surface on those wheels is in the other direction there, then the control wheel will be pulled to the left. So when creating an actual prototype out of metal, it is indeed quite important to ensure the rigidity of the mounting of the CVT disc, especially for using a omniwheel, whereby the rod that it is affixed to should be as short as possible, namely just beyond the centers of these CVT discs to accommodate the full range of motion needed, and it should be as rigid as possible, so probably thicker depending on the kinds of forces involved, and of course the CVT discs themselves will have to be of quite rigid construction for their bearings. With that, we can proceed with the demonstration. So nominally, you would start up the machine at the start of a song, and as you would see here, this left red point here would be measuring the current speed of the system. Ideally, this whole thing here would be locked or decoupled. Let's just do it like so. So let's say that we got up to this point here. You then take hold of the knob in order to further coax it into the correct speed. Then you would lock into position. Of course, we'd have a better mechanism than this. And now we'll be measuring the error. So without control feedback, what will happen is as it gets faster, this whole motion on the right side will, through the torque amplifier, rotate this control pulley over here, and also move this slider, which finally moves our control wheel here. And we can say that this control wheel's position is in effect measuring the error. So let's say that the error would be 0 if it were at this position here, at the middle. And if it's over here, that means that it's starting to get too slow, at least within a certain maximum tolerance. And if it's going over here, it's getting too high within maximum tolerance. So, resuming, as I pedal harder, you will see that the control wheel is moving further toward the left. And as a result, the flywheel on top is rotating ever faster. And you can intuit that it will be able to do this quote-unquote all day, as at least so long as this control wheel doesn't slip, this whole system doesn't fly apart, then it will keep on absorbing more and more energy while never exceeding this amount of increase in speed, measured in distance of the tachometer's displacement. Furthermore, assuming that my Lego prototype didn't have so much friction, especially from the torque amplifier here, then as the system slows down, then we would have the opposite feedback, as you can see here, which is moving the control wheel back toward the right. And if this were working properly, then this would in fact cause momentum to be transferred back from this flywheel into the system in order to maintain the speed. But right now, again, since this is Lego, though we can see over here that compared to the uncoupled case, where, again, it's very easy to stay too fast. In the presence of the control feedback, it is for the most part doing decently well, though with more oscillations than would probably actually happen with a properly implemented metal construction of full scale. It is helping to prevent it from actually accelerating beyond that point. Though technically, with this prototype, there is a chance that the other reason that it's not moving all the way this way is because of reaction forces from the torque amplifier, but hopefully these are in fact minimized. And because this Lego design isn't very great at giving energy back into the system, then we see a lot more fluctuations of this guy moving back toward the right. But overall, this thing here is in fact demonstrating the functionality. And likewise, if I were to have selected a higher speed, then it would require a faster speed before energy starts being siphoned or redirected into the flywheel. And again, here you can also select a slower speed, such that it will react earlier in order to put energy into the flywheel. Another consequence of this mechanism is that, let's say that your system here was happily rotating while in the middle position, then if you were to unlock the control knob, as I'll call it, and you were to do this in order to increase the speed, that would in effect push or apply a force in this direction, which would in turn cause the control wheel to move this way. And as such, instead of only having to pedal harder, you would actually get a bit of an assist from the existing energy stored in the flywheel in order to accelerate the system to a faster tempo in the middle of a song, if you ever wanted to do that for expressivity, or to, let's say, increase hype in the middle of a show. Likewise, if you wanted to slow down this way, when you were already at the equilibrium position, this would pull the measurement head in this direction, which would cause that energy to be automatically absorbed, moving the control wheel to the left. So, yeah, as you can see, this is a very nice and user-friendly hands-off mechanism where, again, assuming that we had a proper metal prototype of full scale with much lower friction compared to the momenta involved, then you'd be able to pedal, and you can imagine that every single time you push down, the energy excess will cause this guy to pulse a bit in this direction, and during the upstroke, the mechanism, per the mathematics that I'm about to discuss, will automatically perfectly move the control wheel to the right by the perfect amount to maintain the speed, at least, to not exceed this motion range. So the musician then would basically be pedaling, and all they have to do is look at the position of the control wheel, or in this case we could probably use Bowden cables to bring the motion or position of the control wheel all the way from the back of the machine to the front console, where they can see that if it's moving too much in this direction, that means that they're pedaling too hard, or simply that they are being able to store energy that will be able to be released later in a more dynamic way, as opposed to the Huygens drive, which is only capable of releasing a constant force regardless of the load. So again, this thing is pretty much a much more advanced method of storing energy and releasing it at the perfect rate, depending on the load. Then, if the musician sees the control wheel steadily progressing toward the right, that means that they have to start pedaling harder. And furthermore, as it was discussed, it is very easy to, in the middle of pedaling, just move this knob left or right in order to change the tempo mid-song. Then separate brakes can be applied to both the system under control and the flywheel when actually winding down to end the song. Regarding the linearity of centrifugal tachometers, here is a simplified analysis of the one over here. In this case, assuming that this offset is instead 0, among other things. So we have these links, we have these weights that would be changing an angle, and we have these masses here for which the centrifugal force trying to pull them back is proportional to the square of the angular velocity. But the spring force here that is counteracting that, of course you have all this trigonometry to do, is only linearly related to this position here. As a result, your final curve is such that it ramps up, and you have this region where it is most linear, and then you have an asymptotic approach toward the maximum displacement. So again, assuming that our speed selection has already been fixed over here, and we're rather talking about the PV head, which is measuring the error, then this can accelerate all the way over here until we reach our maximum speed, but we will never actually reach the complete maximum displacement until, speed is infinite. So yeah, this is not a particularly linear design, though for my mechanism here, that linearity doesn't actually really matter that much other than for maintaining constant sensitivity. Like for example, here, this is where the sensitivity would be the most with respect to the angular velocity, since the slope is the greatest. Whereas if you're operating in this area, the sensitivity would be lower, meaning that the displacement is changing less for changes in the angular velocity. Given that, it is actually possible to solve for a special cam design so that you can have a spring that is pushing linearly, but you are, instead of using these linkages to guide the weights, are using rollers and cams to guide the weights. So in this case I have to, I think this was probably the curve for when I don't incorporate this initial linear shape or linear guide, as you can see here, if the slope is initially 0 and we are rotating or accelerating the tachometer, then there will be no force available to start compressing the spring. So in that case you have to make a compromise, and thus at the most low speeds it won't be perfectly linear. But after that, then we can apply this curve here, so you'd have your truss work to kind of like help support that shape. And now the speed relation between the angular velocity and the actual displacement will be perfectly linear. These curves were from when I was just confirming that my math was actually working. That would be a bit complicated to construct, but really the only point of having a perfectly linear centrifugal tachometer is to have consistent sensitivity, and also so that if you wanted to, within the machine, have a scale displayed in order for you to select the desired tempo, then that scale would actually be linear instead of following this weird curve. Lastly, I'll be covering the mathematical theory behind why this CVT mechanism works and why the control implications are actually quite powerful. So first let's look into this configuration A, where we have a CVT disk and just this control wheel that is directly connected to the flywheel. So in this case we have S referring to the system under control and F referring to the flywheel or control battery. So here I can set the initial speed or the target speed. Then we have the radius of the control wheel. This stuff here is regarding the ratio of the speed of the system under control versus that of this flywheel. So if we increase the, or it's more so, I think this was a gearing down. Yeah, so if we increase this, then that's implying that we have a speed up between the power input, or at least the programming wheels, and the actual tachometer, while increasing this implies a gearing down for the flywheel, so where the flywheel gets slower and slower. With that, I end up having a bunch of involved or semi-organized calculations. So like here, this is the actual current gear ratio. Then stuff about the actual density and total moment of inertia of the giant flywheel Martin was proposing, assuming it were made of foam. As it so happens that if it were to be made of foam, that would in fact be quite sufficient for my design. And of course, much safer and more practical, while still being able to look cool. So yeah, 1.25 meter radius. And this is the ratio of the effective moment of inertia. So if we gear the flywheel to rotate faster, then that would imply a greater effective moment of inertia. That's with respect to the total moment of inertia of the programming wheels, which I was estimating. And then we get into the whole conservation of energy calculations. But the important thing then is that basically, if the control wheel is moving in a certain direction, then it is predicted that the force or torque on the system under control, and likewise the flywheel, so hence the momentum transfer, will be linearly proportional to that velocity. And in this case, with the way this system, or rather this system, was set up, the velocity of the control wheel will be directly proportional to the rate of change of the error of the speed. So this is in effect implementing a kind of derivative control. Now in the simulation, I was able to do a simulation of what happens when you have a constant torque input or a constant frictive load. Let's just turn these off for now. So looking at this orange graph here, which is the speed of the system under control, and this red one, which is the speed of the flywheel, if we assume the velocity here to be positive in this direction, and time moving in this direction, then this means that we would predict that when moving from the midpoint, expectedly, you would have an asymptotic decrease in the speed of the system under control as more and more energy is put into the flywheel. And if we increase the velocity, that will also scale, in this case a time. You can see it would take a shorter amount to reach this point here, which is, well, I guess if we were to go back into reverse. So in this direction, that means that the control wheel is now moving toward the center, and thus we are transmitting energy from the flywheel, assuming that initial velocity of the system, and hence that initial energy in the flywheel. That energy is being transmitted back into the system up to a maximum until we have crossed the center and it starts decreasing again, in this case symmetrically. And this here is showing the point of maximum acceleration, or basically the point of maximum sensitivity. So yeah, it would have been a bit complicated to tune the parameters so that the point of maximum sensitivity would also be at the midpoint, among other things. Anyways, so let's say that if you had an increasing input force, and you can see here the peak ends up somewhere else, and if you had a certain amount of friction, then it would be implied that you would need a certain curve for the motion of the control wheel in order to maintain a constant speed. So in terms of sensitivity, the basic concept then is that if the torque at a particular position is greater for the same velocity of the control wheel, as in the same movement velocity here, then we would say that it is more sensitive at that position or for that configuration. So in this case, if you want to optimize the sensitivity, or you want to put the position of greatest sensitivity at a certain part or location, so in this case here, this black graph is with respect to the displacement of the control wheel, and here its maximum is indeed roughly at the midpoint, then you would simply analyze this graph here. So yeah, again, initial or instantaneous angular acceleration for changing initial contact radius being this guy here, RC, and that maximum, in this case the magnitude, depends linearly on the actual velocity, but it will change in position based on the ratio of the moment of inertia of the flywheel compared to the system under control. Then if you look at this curve over here, which was supposed to be the naively calculated total angular momentum of the system, for whatever the reason, momentum was not being conserved, even though I was conserving energy. So yeah, that was confusing me, and as a result, I came up with this design here, so that instead of having to deal with these perpendicular axes, the two items that I am conserving are in parallel. But then even with that, I still had issues until I realized that basically the magic of why I'm able to get a wonderful or very large torque in transferring momentum between these two disks was due to the fact that this whole CVT system is actually being coupled to the Earth, or in this case a very large mass. So when I was doing the calculations for that, it so happens that indeed if you make the mass of the Earth or its inertia very large, then the term for that ends up canceling out, or yeah, basically just approaching zero, and that leads us to my original style of analysis where I didn't account for it. But if I do account for it, even if it's very large, then once I add things up together, then the calculated total energy and momentum will indeed be constant. Given that, you'll see now that it makes sense that as we move to the left and approach the center of the flywheel CVT disk, the force, or the torques, would actually, and hence the speed, would actually greatly increase. Now for the analysis of configuration B over here, instead of using a control radius increasing in this direction, I used a control wheel position. So 0 is over here, and at the midpoint, that position would be just minus 0.1. So now the velocity of the control wheel would be positive in this direction. And in that regard, if we have the velocity be positive like so, then expectedly, as we move this control wheel to the right, then there will be a momentum transfer between the flywheel and the system under control that will peak once the flywheel has come to a complete stop as a result of this being at the center here, like so. And that peak will depend on the mass of the flywheel. Well, yeah, here I had a fixed ratio, but if I were to increase that by tenfold, you can see that the peak will increase. So that means that the flywheel will be able to restore a much greater energy deficit or losses from friction. Or alternatively, we can just make the flywheel spin a lot faster, like so. And then, if we were to move the control wheel in the opposite direction, then, as we'd expect, unlike in this design here, where it only asymptotically slows down, we actually come to a complete stop if we reach this point here. And that's like so. So now, bringing the velocity back here, what I want to direct your attention toward is this curve over here. So this was the counterpart to the black curve here, which was demonstrating the point of maximum sensitivity, whereas here with this curve we can see that we have our minimum sensitivity always at the midpoint between the centers of these CVT disks. But to either side, so here you can see this peak here, if we make the the flywheel heavy enough, or we make it spin a lot faster, like so. So again, this is just increasing the speed between the programming wheels and the CVT discs. And here I'm simply not doing any gearing down from the CVT disc or the upper CVT disc to the flywheel. Then at either side, we end up having this extremely steep, basically asymptotic increase in sensitivity, meaning that the further we get away from the target speed, the more torque this mechanism here will be able to apply to counteract it. As for why this curve is shaped like this, intuitively in this direction, you can imagine that as the control wheel moves over here, if you're already at the target speed, then that implies that the flywheel is already moving ever faster and faster. Therefore, the momentum transfers involved at your given control wheel speed will be ever greater. Likewise, in the converse, my preferred interpretation is that if your flywheel is stationary, but it has a very high inertia, and your system is already rotating or moving at a certain speed, then if you suddenly move the control wheel into that high inertia upper CVT disc, then expectedly, as the inertia of this flywheel is increased, then the torque required to get it to suddenly start moving will be ever greater. So that's why we get this almost symmetrical curve. And again, this sensitivity here is regarding the derivative control feedback, because the control wheel velocity is directly proportional to the rate of change of the error here. So if you're familiar with what derivative control is, so compared to proportional control, where the restoring force toward your target speed is directly proportional, instead the force is acting to prevent a change in this error. So if your speed is already here, then if you have a very strong derivative gain, then if it detects a acceleration, then the derivative control will try to stop or slow down that acceleration. So instead of, for example, your curve looking like this, your speed curve, you would try to turn it into this, if not completely stop it. So in the case of fully derivative control in the absence of proportional or integral components, then if your gain curve were completely flat, then you would only be able to constantly move the speed this way and that way depending on the magnitude of the disturbing forces or loads without actually being able to maintain a specific target speed. But if your derivative gain curve is shaped like this, then depending on the relationship between the position of your control wheel, so again, here we have our dimensions of 0.2, just for reference, and the position of your PV head here, which is measuring the error, then let's say that if a motion of just 0.5 centimeters were to be able to cause the motion of the control wheel to move all the way here, then that would be completely prevented by the presence of this huge derivative gain preventing increases in speed, or basically causing a huge damping. And that whole damping is once again being facilitated by this whole CVT mechanism and the absorption of energy and releasing back of energy to and from the flywheel. So thus follows that the more motion amplification you can implement through this torque amplifier and pulley system, the much smaller the deviation in the position of the centrifugal tachometer you will need in order to reach these extremities of the derivative control. But you can only take advantage of these parts of the derivative control if your CVT mechanism here and this omniwheel is capable of supplying that torque, else it will slip. Or the CVT mechanism and whatnot would be spinning so fast that it would break apart. Otherwise, you can see then that there's actually the implication that if the musician keeps on pedaling harder and harder, they can bias the control wheel to sit within this area where the flywheel is spinning more quickly and the derivative control sensitivity is much higher. So though there would be this small deviation from the target speed, it would be much harder to push the machine out of that point, and so you would actually have a much lower standard deviation from this particular area. So the implication then is that unlike the other suggested control methods, here the harder you pedal, the tighter the music will be, just that you'll have to keep track of the position of that control wheel here and the implied deviation in speed from the nominal target speed over here, which would correspond with the position of this set point head from the speed control knob. It should also follow from this derivative gain curve that there is no need for any proportional or integral control. That is because, as you can see here, we already have an increasingly increasing, mind asymptotically so, derivative gain as we get further away from the set point or target speed. Likewise, we do not need any integral control to settle upon the set point, since we instead rely on having this finite, let's call it a derivative well, that we cannot get beyond, and we simply need to maximize the motion amplification or gain here in order to make the effective tolerance range for the motion of the centrifugal tachometer as narrow as possible. Lastly, if ever we change the set point by moving this set point head, this will necessarily cause the control wheel to move and automatically and proportionally, mind again, asymptotically, induce the counteracting derivative gain forces that will apply the torques needed to bring the system under control toward that new set point. Alright, that's it for this video. For those interested in seeing the process of building this machine, see the upcoming video. And for those who found this content interesting and are interested in matters of mechanical engineering, especially regarding typewriters, feel free to like and subscribe.